Hey there YouTube. I wanted to show you my little kiln that I rewired and I set up to run with a Raspberry Pi digital controller. I picked up this little guy for about 300 bucks on Craigslist. It worked out of the box, but it used really old tech. You can see the old temperature meter right here, and all this did was read. This isn't even hooked up to any electronics or nothing. It just read the voltage across the thermocouple, and it was an older thermocouple. And then it was a open loop controller, so it just had this oven knob that you set, and it's just old contacts in here. It kind of falling apart now, but that's what all that the amperage was running through was that guy. I mean, it worked, but it wasn't real accurate. It's accurate as far as this, but I wanted a project to do something with the Raspberry Pi, and this dial was down here on that kind of thing. So I rewired it. I'll show you the rewiring, and I'll do a diagram to attach with it. I wrote software for the Raspberry Pi to deal with reading the thermocouple via right now it's just it's using an Adafruit breakout board for the Max 31855. It's a K-type temperature probe. I'm not happy with the temperature probe because once it gets to about 1,000 degrees, it starts having issues. I ordered a much better probe from Omega Engineering. I think that's what they're called, Omega, maybe it's Thermal Engineering. Anyway, if you look up Omega thermocouples, you'll find them all over the web. Supposedly it's much better and much more stable at higher temperatures because it's better quality. This is just some cheap Chinese thermocouple. Anyway, it works up to a point, and then it starts giving on here the Max 855 starts giving some weird readings and stuff. So to turn it on, plug it in, I hooked up let me zoom in on here so you can see the screen start up. Sorry about this. I just want to so you can see. Okay. So this is written in, and it's not level, and then people are going to complain and go, it's not level. So here, I'll try to level this stupid thing. Okay, there. And it's drifting a little bit. Anyway, that's weird. I wrote this in PtQt, so that's Python's, it's a library for Qt, which is a graphical cross-platform library GUI system. This is all touch, so this is the 7-inch Raspberry Pi touch display. I'm probably going to rearrange these a little bit. This is just a touch spinner, and that works. You can also just touch this and enter the temperature there. It's set so that I can set the current target temperature or the set temperature, and then I can control whether the kiln's on or off. So if I hit on, I put a little graphic in here too, so that switches to show you that it's on. Not sure if you can hear it, but you can actually hear the heating coils in there. You'll start to see it heat up in a second as those guys heat up. I wanted this completely controlled from here, so I didn't really have to muck around, especially if my family wanted to come out and fool around with it, and it wasn't, it was just pretty straightforward. It's not as straightforward as this, but it's pretty accurate. You can come out and set that temperature, and it's going to go there straight away. I'm not happy with, well, I shouldn't say I'm not happy, but I know that I have to do more work on the PID controller part of this. And PID, for you, those people that don't know, is proportional, integral, and derivative control. And right now I'm just using if statements. And this has enough thermal mass that using if statements gets you close. Especially at the higher temperature ranges, it's so slow in response that if statements, you in your code for saying if it's at this temperature, shut it off, they work pretty well. And I found that probably about above, there's a point, and I'll show you a graph, I'll probably put it in right now, but you'll see there's a point, and it's probably a little over 700, 800, where the graph just kind of tips over, just kind of bloop. And once that happens, the if statements work fine because it's so slow in response. So, but up to that point, there's probably a good, depending on where you're at, up to a 20-degree overshoot before it kind of settles back down. But those are pretty low temperatures, and I don't know that I'll be doing anything with it at those low temperatures. But as an exercise, I'd like to do the PID more proper. And what that means is at this point, this just has if statements that turn off a solid state relay, which I'll show you in a minute here, and that's it. Just set, and it uses a general purpose I/O pin on the Raspberry Pi to either have a voltage, a DC voltage on that relay, or nothing, and that allows the AC to flow or not. What a PID controller will do is it will use, I think there's one pin or maybe two on here of the GPIO pins that will do PWM, which is pulse width modulation, which you're going to have to look it up on Wikipedia or whatever, but essentially you say you're going to go on, a period of time is here, and you're allowed so much of that is called a duty cycle. You're going to be on for this long. So when you use a PID controller, you set, for something like this, you set probably a pretty long cycle time, and you say of that time you're going to be on 50% of the time, and that's based on what that controller is giving back to you, and that's based on the error, and the error is what's the difference between the current temperature and your target temperature with the modification of your PID controller, which is a proportional amount of that error, an integral amount based on that error, and then a derivative that's based on the time differences there. So what happens is essentially your program reads the temperature. It does it every second. What I'm having to do here, every second it'll read the temperature. It'll go see where is it at, where should it, what's the set temperature, where should it be, gets an error amount, sends it into a PID function that I have access to one. I got to rewrite it a little bit. It gets a number back that says you should raise the temperature this much more. But what it really means is that you're going to pulse. If you're getting close, if you're far away from your temperature, you're just going to be on. So your duty cycle on your PWM is going to be 100%. You're just going to be on. So for every time cycle, it's just on 100%. So it just stays on. But as you get close, you want that curve to kind of start curving to get to your set temperature. To do that, you start pulsing, and you shorten the duty cycle on your pulse. So you're shortening the duty cycle until you get to zero. You get close enough. There's some little, epsilon in there that you're saying, okay, if you're below that, then just shut it off because you're going to coast right in on the temperature. And then as, it sits and watches it, it just kind of bumps it up every now and again with a little bit of a pulse to keep it at whatever temperature it needs to be at. So that's where I'm going to be headed with that. So anything else with that? So I guess the two main things I still got to do with that is I got to figure out the PWM, which pin it was. I've looked it up and stuff, but you know how it is. You go off and do something else and you forget a little bit. So I got to come back and do that. And then that PID controller, I got to get the right, make sure the code comes in right as a percentage and all that. I've done some testing there. Then the other thing with PID controllers is there's weights to the three things, to the proportion, the integral, and the derivative amounts. There's weights that get applied to it, and monkeying with those is called tuning. So I'll have to do some tuning with it. Now I did develop in MATLAB a model of this that's really accurate. It's a state space model, but I guess I got to learn how to implement that. And I'm not too sure if I want to go through the work of doing that. It might help with the tuning, or I can just muck around with the tuning and get it close. I'm not sure at this point. And I did find some stuff where people talking about, well, don't muck around with tuning, just do, you know, there's like some algorithms out there to help you figure that out. So that's what I'll give it a try. So I'm going to turn this around. I got the cover off so I can show you the wiring and stuff here. Okay, turned around. So we have our mains coming in here. Yes, this is running on mains. It's 120, so it can hurt you. Probably not kill you unless you do something really stupid, but it certainly can hurt you. So if you plan on doing something like this and you're not comfortable with mucking around with mains voltage, I would get the help of, you know, an electrician or somebody that knows what they're doing with this stuff. You want to know what you're doing. So essentially your mains come in. I split it across that switch. That's a 15 amp switch. So at this point, this is 1800 watts at 120. It's 15 amps. And I haven't actually measured the amperage, but I'm sure it's well within that range. So it splits. So one leg comes in, splits across that switch, hits the other side. On the other side of that switch, the light, one leg of the light hooks up, and one leg of my heater hooks up. And also, I have this guy here wired, this outlet down here wired through that switch as well. So there's three things connected to that switch there: the light, my heater power, and then this power. And then, so then if we follow that power, say through the heater, it goes in there on this side of the heater coil, comes out on this side, goes up here, goes in that side, comes out here. From there it goes in and it connects to the solid state relay here. And then on the other side of the AC solid state relay is the other leg on the mains. So this is just a switch, just like that, right there. And so you just got two switches. One is manually controlled, one is solid state, and it's controlled by these little wires going up here. That's DC wires going up to a GPIO port and the ground on the Raspberry Pi. The red wires are just the grounds all tied together on everything. And then these lines here, they go out and up to the Raspberry Pi, and they go up to this little breakout board. This is the Adafruit breakout board for the Max 31855 thermocouple reader. And this is just temporarily kind of put in here until I get my good thermocouple. I didn't want to do a lot of work with that yet. And I also at some point want to get this meter going again. I think it'd be neat to have that. And since it just reads the voltage, I can just put it in parallel with that and should read fine. So the wiring is pretty straightforward and simple. The wiring up here is a little bit more complicated because this breakout board up here uses the SPI interface, SPI interface on the Raspberry Pi to talk to the Mac's chip. So the Raspberry uses SPI to talk to it. So that's 3. You have master in, slave out, master out, slave in, and your clock. And then, of course, the board needs power, so there's a ground in 3.3. So you want to be aware of that. So this is running at 3.3, and then this guy's controlled at, this is 5 volts. It'll run at 1 or 3, but I figured I might as well put it to the 5 and, you know, just make sure it's on and off. So that's the gist of it. This is just the power for this, and since it runs through there, I am going to put in another heating coil that'll go on the top, so it'll go up on top up here. I'll have to put it in there and drill some holes. I'm not entirely sure. They're probably going to have to be up in here somewhere, pretty high. Anyway, so that'll just be another heating coil to go here, and then I'm going to put in another solid state relay for that one. This will take up to 40 amps, but I figured it'd be nice to have 2, because then once I reach temperature, because it'll help heat it up a lot faster. Once I reach the operating temperature, then I can not run one of these and save a little bit of, you know, money on the power bill, and just use one to kind of keep it at the temperature, whether it's that one or the top one, I don't know. So that's my rewired little kiln. Now I'm excited to give it a try on some projects, and we'll see where it goes from there. And if in case anybody's wondering, this is a Skutt electronic kiln. It's really, really old. There's no date on it, but like the serial number is 52. So, you know, it's pretty old. But it still works. The bricks are in still good shape, so far I'm happy with it. You can leave questions or comments down below. You know, if you want to rag on me about, there is a cover that goes on here, so don't rag on me about that. It goes here. Like so. And if you're an electrician and you want to yell at me about using a wire nut, one of these things instead of, I don't know, whatever technique you prefer, well, go for it and cite all your safety codes or whatever you want to me. But I think that's what's the problem in the country today. We got so many people that are so concerned about safety, and you don't know what the hell you're doing and blah blah blah, that anything that's just common sense goes out the window, and you're not allowed to do anything. And it's just, you know, when people get mad about the nanny state, that's the issue. You know, look at my garage here. Let me zoom out here. I do all kinds of shit in my garage. See, here's my little mini kiln I just got. I suppose I'm not a fucking forge master, so I shouldn't have that. Maybe I need a vacuum cleaner license for that. So doing wiring for something like this, yes, you should know what the hell you're doing, and you can find out and read lots of stuff. And this isn't plugged in all the time. It's supervised. It's away from stuff, so even if the damn thing starts on fire, you know, it's probably not going to be that big of a deal. We'll put it out. I have a fire extinguisher. I know how to use one of those too. So, I'm sorry, I just get irritated when people want to say that, oh, you can't know how to do any of this. You know, frankly, the wiring in my house was done by a licensed electrician, and I think he was drunk because it's the shittiest wiring I've ever seen. So I just do it myself. I live in, you know, a rural state, and it's not like you can just get somebody here, like, call them up on the phone. And generally when they do, it's $200-300 an hour. It's absolutely ridiculous, and then you're hoping you don't get the drunk one. So I'm sorry for the rant, but you know, it seems on YouTube there's always some asshole out there that's going to say, yeah, that should be
frickin' 18 gauge, thermal resistant, you know, type C, and you're using type A, and that's just gonna burn up, and then your whole house is gonna burn up. Whatever, it's my fucking house. Shut up. Go troll somebody else's, go get a life, go do something other than fucking be an internet troll. So, whatever. Anybody else wants to comment? Or ask questions, or if they want to do it, hey, I'm open, so thanks.